Hi, this is Dave Nguyen, and in this video I'm going to explain Pavlides template matching, or PTM, and how it applies to data from the planarized globe plot, or PGP projection. So part one will be explaining Pavlides template matching. Pavlides template matching is the same as the Pearson correlation coefficient. Here's the equation. I'm not going to describe how it is calculated. Please refer to, or I refer you to, the YouTube video by Eugene O'Loughlin that is linked to in the README info of the script that goes with this document. Here I've included sample data in this document, and all the sample data is available on the GitHub folder that goes with this script so that you can practice and replicate my data in order to familiarize yourself with the automated script. So here I picked just data from the internet, two data sets that are correlated, as you can see how the dots line up from up and down. And when we run these this data, right, the profile on the x-axis and profile on the y-axis, when we run them through the automated PTM script, right, the value that comes out is minus 0.87, which makes sense of how this data is distributed. You see how the data lines up in a relatively straight line, and it goes from upper left to bottom right, meaning it's a negative slope. In data 2, I selected these two data because I know that they're not correlated, as you can see by the scatter of the plots. Okay, no one straight line. They don't fit well upon a straight line. And when you run this sample data 2 through the script, it gives a PTM coefficient of minus 0.006, as in no correlation. Pavlides template matching was created by Pavlides and Noble, and here's the reference, okay, to their paper. Okay, so I included other sample data to give you an idea of what PTM measures. So in this case, sample 3, we compare two profiles. One is the template, that is a series of 5 zeros followed by a series of 5 ones, which gives us this step up. And I compared it to just this data that I just made up, all right, to show you that when you run these two data sets against each other via PTM, you get a coefficient of 0.93. Okay, so a coefficient of 1 means a strong perfect correlation. -1 means a strong negative correlation, and 0 means no correlation. So in this case, these two profiles have a strong correlation of 0.93, which is close to 1, right? And this goes to show that PTM measures the overall pattern of two data. Okay, it does not measure the magnitude of the data, because clearly here you see the orange data, right, have much larger values and a larger jump than the blue data, right? But yet the correlation is 0.93. And if you look in sample data 4, here I just switched the order of the orange points such that instead of a climb, it's a drop. And here, when you run this through PTM, the script that I wrote, you get a correlation coefficient of minus 0.93, which is the opposite of sample data 3. And that makes sense. Why? Because the orange data in both these cases are the same, except I switched the order. Instead of a climb, it's a dip. And this dip is the opposite pattern of this blue rise. And therefore, you have a minus 0.93 here, but a positive 0.93 here. All right, now let's look at sample data 5 and 6. Sample data 5, the template in blue here, right, has two bumps. Okay, you bump up, down, and then bump up again. And here the data in orange also has two bumps. Okay, and the correlation coefficient between these two profiles is 0.83, which is still a strong correlation. And here in sample 6, I purposely made the first bump in the orange dampened, so it doesn't jump as high. Okay, while the second jump, right, is just as high as in sample 5. And here what the result is, a weakened PTM coefficient of 0.68 compared to 0.83. Why? Because the first jump, okay, isn't as high, okay, as in sample data 5, but still there is a slight bump, and therefore this overall pattern of the orange still matches the pattern of the blue. In sample data 7 and 8, here I purposely also using a blue template that has 2 bumps. Okay, but in the orange data, I purposely remove the second bump. So there's only the first bump, it comes back down, and this stays flat. And this gives a correlation value of 0.55. And in sample 8, what I did was I just switched the bumps in the orange, right? Position 4, 5, 6, I switched with 10, 11, 12. So now the bump's back here instead of in the middle. And these 2 profiles have a correlation of 0.55, the same as in sample 7. And that makes sense because all I did was switch these samples 4, 5, 6 with samples 10, 11, and 12. As you see, these 2 profiles are obviously different, right, to our eyes, but their PTM coefficient is 0.55. It's the same because, again, PTM measures overall similarity in these patterns. Okay, in this case, the bumps in the blue data. And then in sample 9 and 10, here, sample 9 and 10, they're the same, except that in sample data 10, the orange data, right, I've added a value of 4 to each of the points. So it's higher up, as you can see, compared to 9 and 10. But guess what? Compared to the same blue template profile, they have the same correlation coefficient of 0.83, 0.83, even though sample data 10 has much higher values than sample data 9, but it has the same exact pattern as sample data 9. Again, this goes to show that PTM measures the similarities in overall patterns, right, of 2 profiles. It does not measure the magnitude, okay, of the profiles. The sample data here compare the profile in orange to a blue profile that has only binary values. That is, you have zeros and ones and zeros and ones. PTM also works by comparing 2 profiles, both of which are like the orange one. That is, they are continuous variables that can be integers and integers with decimals as opposed to just binary zeros and ones. And that's exactly what we'll be doing when we compare 2 PGP profiles. So part 2 is how to apply PTM data to PGP data. So what is PGP data? The planarized globe plot, right, is a 2D system to visualize a 3D system, right? So here, if you have a 3D sphere and you divide the sphere into sectors according to these degrees here, divide the sphere vertically from 0 to minus 180 on the left and 0 to positive 180 on the right. And you also divide it horizontally from 0 at the equator to positive 180. And then the other side is 0 to negative 180. And when you do that, you divide the sphere into here at least 8 sectors, okay? And these 8 sectors can be flattened out into this 2-dimensional system, which we are all familiar with because we're used to interpreting things in 2 dimensions. And here I've numbered each sector by color coding and number, and I've also kept the color coding and number here on the right. And I've numbered this sector in the front here. If you're looking straight at this sphere, upper left is 1, upper right is 2, bottom left is 3, bottom right is 4, and then 5, 6 in the back, 7, 8 in the back. All right, and so it's important here to recognize that this numbering system is arbitrary. I just happen to choose 1, 2, 3, 4, and then 5, 6, 7, 8. But you can choose any numbering system you want. You just need to keep this numbering system consistent across all your samples. So the PGP projection flattens a 3-dimensional sphere into a 2-dimensional plane. So the PGP projection shows points in 3D space, okay, as dots that have 3 dimensions in a 2D space. So the first dimension is the vertical coordinate, right, which is the line that divides the sphere vertically. And then the second dimension is the horizontal coordinate, which is the line that divides the sphere horizontally. The third dimension is the distance between any point in this 3D system. So you can have a point inside the sphere, on the surface of the sphere, or outside the sphere. But every single point in the system has a distance from itself to the center of the sphere. And that distance is the third dimension. In this case, the third dimension will either be a color intensity or a marker size. For a little bit more detail on how we turn the XYZ coordinates okay, from our imaging data to data in the PGP projection, we convert Cartesian coordinates of x, y, z for every 3D point in space into the spherical coordinates of r, theta, and phi. But what we plot in the PGP is not r, theta, and phi. What we plot is phi, this angle here, the angle gamma between the y and z axis, and then last we plot r, which is the distance between every point to the origin, right? And so PGP data converts x, y, z coordinates into phi, gamma, and r, the magnitude, as the 3 dimensions. So in this way, every square here will have a bunch of data points in it. Since each data point has 3 coordinates, a phi, a gamma, and an r, we can average all the phi's, all the gammas, and all the r's in each square to get one centroid that has 3 coordinates, phi, gamma, and r. Right, so we find the centroid of all points in each of these sectors. So if a PGP system has 8 squares, 8 units like this one, and each unit has 3 coordinates, phi, gamma, and r, or the magnitude, then that means there are 8 times 3, okay, or 24 values, okay, in a profile. Okay, a PGP profile of 8 squares has 8 times 3 equals 24 values. Okay, now an important point is that the PGP unit system doesn't have to be just 8. In fact, you can divide it further, divide each of the 8 into 4 squares, and what you have is a 32 unit system. And here I just numbered it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And again, this is just my convention. Okay, this numbering system is arbitrary. You just have to keep it consistent in yours. And in the automated script, I coded it to go along with this numbering system. So in this case, instead of having only 8 sectors, we have 32 sectors. In a grid system that has 32 squares, each square will have 3 coordinates, phi, gamma, and r. Therefore, 32 times 3 is 96 values. So if you do PGP, okay, on a 32 unit system, your profile, okay, of your 3D object will have 96 values. Okay, apply the PTM analysis to PGP data from an actual 3D model. Here with these blue and red dots, I've modeled a process called epithelial to mesenchymal transition, which is a process in which epithelial cells go from being polar, that is, they have a front end and a back end, all right, like a north and a south, that is defined by the location of specific markers, okay, or say organelles on one side and not the other. And as this cell goes through EMT, it starts to lose this polarity as the markers start to mix, and eventually when it's done with EMT, the markers are distributed evenly across the whole cell as opposed to being separated on one side or the other. Now, I want to point out that these dots, okay, PGP data and PTM data can work on data that are of any shape, okay, not just dots. I just happen to use dots for simplicity. These dots can represent organelles in the cell, or they can represent points on the surface of any 3D object. Having said that, in this case, okay, sample data 11, what we're doing is we're comparing the PGP profile of the blue dots versus the red dots. And here's the blue dots. This is what the PGP transform of this 3-dimensional shape looks like. And here's the PGP projection of the red dots, okay? And if you run these two profiles against each other in the PTM algorithm, what you get is a coefficient of minus 0.05, meaning there's no correlation between them, which makes sense because these red dots and blue dots, they occupy different places in the same 3-dimensional sphere or 3-dimensional system. It doesn't have to be a sphere. All right. And here in the mid stage, okay, if you compare the PGP of the blue dots to the red dots, right, again, the correlation coefficient is near 0, okay? However, when you compare the blue dots to the red dots, okay, in the late stage, here the coefficient, right, becomes 0.18. Okay, that is the pattern of distribution of blue dots and the pattern distribution of red dots, right, in this late stage. Okay, starts to show, okay, some similarity to each other. Now, I want to point out that these correlation coefficients, okay, the goal isn't to have them to be near 1, okay, because typically when you run a correlation, the closer to 1, that means the stronger the correlation. Okay, in this case, we're measuring two patterns as is, and so we take at face value what the correlation is. We want to compare correlations between comparisons, okay? And so just because a correlation value is not near 1 doesn't mean that the PTM approach is not working. Okay, so now in this figure 6a, I'm comparing the three stages with each other. Here we're going to ignore, okay, blue and red. Okay, here I plotted both blue and red in the same PGP plot, okay, for early. And then here's mid stage, okay, plotting both blue and red. We're ignoring blue and red. Everything belongs to the same group. And here's late stage, again, ignoring blue and red. We plot both together. And now we're going to do PTM, comparing these three stages to each other, early to mid, early to late, and mid to late. And here's the data. If you compare early stage to mid stage, the PTM coefficient is 0.4. Early to late is 0.19. Mid stage to late stage is 0.18. And I'll let you look at this document yourself, but I'll point out here that you will find that the numbers, the magnitude of the PTM coefficients, for these comparisons aren't intellectually satisfying in light of how different we know these images, right, these stages to be, early versus mid, right, mid versus late. Okay, and I'm showing this to you on purpose because here we've defined the origin to be the middle of the points. Okay, this orange dot, the origin. Okay, and I purposely show this to you to inform you that though it's intuitive to put the origin at the middle of your 3D system, this position isn't always the optimal place to put the origin. Because in the next figure, figure 6b, what I did is I moved the origin, this orange dot, to be outside and at the front of the 3D system. Okay, so in each of the same three stages now, I moved the origin from the middle to the right or to the front, okay, of the object. And here what this does is it drastically changes the PGP profile, right, of these three systems. Okay, previously, this is what the PGP profile of the early stage system looks like if defining origin at the middle, okay, and grouping both blue and red together, all right? But see what happens. Compare this PGP profile, okay, to this one, right? When it's the same system, but we just move the origin to the outside. And what happens is that if the origin is here, then all the dots are now located in the back part of the sphere. That is quadrants, if we divide into 8, 5, 6, 7, and 8. Thus you see a lot of the dots, right, are in the outer 4 squares and none in the middle 4, because the middle 4 represent the front 4, okay, of the system. But here, if the origin is here, the front is here in this blank space. There are no dots there, okay? So not only does moving the origin drastically change the PGP profile for each of these three stages, okay, when we run PTM analysis of these PGP stages, or PGP data from these three stages with each other, it drastically changes the PTM coefficient, okay? Previously, the PTM coefficient was here, what, 0.14, 0.19, 0.18. But here, by moving the origin, right, we change them drastically, okay? And now, these new PTM coefficients make a lot more sense of the differences we see in each image. And I'll leave it to you to look at the paper, okay? But I want to show you this to prove the point that where you place the origin is an arbitrary decision, okay? And it's not a straightforward one. And depending how complicated your system is, it might require a lot of careful thought as to where you're going to place the origin. And you may want to place the origin in multiple places, okay, for the same two groups you're comparing, and then to see which one gives you the most difference, right? Because say your two objects that you're comparing might actually have spatial differences in 3 dimensions. However, if you place the origin at a suboptimal place, then the PGP projection and the PTM analysis won't show you that difference. And it's not because the difference isn't there. It's because you haven't picked the optimal origin, okay, to best accentuate the differences. So in summary, the takeaway points is that 1, the number of grid units, okay, can be expanded, okay, beyond 8. In the automated script on GitHub, I coded it to use a 32-unit grid system, okay? And 32-unit grid system, each unit has a centroid of 3 dimensions, so 32 times 3 is 96 values, okay? So if you do PTM from data from a 32-unit system, then your PTM profiles you're comparing, each profile needs to have 96 values, okay? All right, second takeaway point is that the placement of the origin of a 3D system is arbitrary. Again, this has pros and cons. The pro is that it allows the researcher to define the origin, okay, at a point that is most scientifically meaningful relative to the question they're asking. Are you measuring the spatial information in 3D protein structures, right? Or are you measuring the 3D spatial information of apoptosis, right? Because as a cell undergoes apoptosis, its organelles begin to disintegrate, and as it progresses on, right, you start to lose the traditional, physical markers or organelle characteristics, right? Because everything's being degraded. And so you would need to define, in the case of apoptosis, a scientifically meaningful origin, okay, that allows you to consistently compare the early stages of apoptosis with the late stages of apoptosis. So the con of this is that different origins can drastically change the PTM results, okay, which is why you need to analyze your data, okay, with various origins, okay, and not just assume that the center of the 3D system, right, is the optimal place to put the origin. Third, you want to be consistent about the following things across all samples and between experiments, okay, that you want to compare with each other. 1, you want to be consistent about how you number the grids in the PGP projection. Again, the automated script that I coded goes with the numbering system that's in this document, that is figure 4. All right, another point to be consistent about is the number of grid units in the PGP projection. In this case, it's 32 for the automated script. And lastly, you want to be consistent about the placement of the origin in the 3D system, right, or 3D object. Again, the location of the origin is arbitrary and can drastically affect the differences that you find or don't find. Lastly, I'd like to point out that I have 2 different GitHub scripts, okay, for this entire process. The first one is to just run create the PGP plot, okay, from your XYZ data. All right, and I separated this because some people might just want to plot their XYZ in a PGP projection, and they don't care about the PTM. All right, and so they can just use this script. Okay. However, after you get the graph from running this script and the output file, you can select certain columns from that output file and input it into the second script to get the PTM values, right? As we did in this video, I compared a lot of different 3D structures, and I showed you their PTM value, okay? And so I separated 2 different scripts, right? So that people who just want the plotting don't have to go through the hassle of running the PTM analysis too. Okay, there you go.